All right. Hello, everybody. Obviously, I can't make it today. I'm going to be on jury duty today, so I wanted to make a video for a last couple of applications for exponential functions. And so just want to get started right away. Did one yesterday involving an exponential growth, and I'd like to just get started today with an exponential decay example. Now, the equation for exponential decay varies just slightly from exponential growth. It starts off with a sub t, which is still going to represent the amount at time t, a sub 0, which represents the initial amount, a 1, an r, which represents the rate expressed as a decimal, raised to the t power, which represents, of course, time. But instead of a plus in the middle of the parentheses, when it's exponential decay, it turns into a minus. So this is the equation everybody wants to have down for exponential decay. And now I'd like to just run through an example of how to apply exponential decay. All right, so here's the example. What we're going to do is we're going to buy a brand new truck. And a brand new truck costs approximately, depending of course on model and what you include in it and so on and so on. But a brand new truck, I just happened to look up what I would want if I had won the lottery. And a new truck that I would want with everything on it costs approximately 65 grand. Of course I can't afford that, but you can always dream. I gotta remember to play the lottery once in a while. Okay, but if we take that $65,000 truck and we start to drive it, and we drive it and we drive it, of course, what happens to vehicles over time is they lose value. All right? Now, a new truck actually maintains its value fairly well, but it still decreases at a rate of about 9% per year. About 9% per year of the value of the truck is lost as you drive it year after year after year. So, my question for everybody is, what would be the value of our truck after 5 years of driving? Cost $65,000 brand new, and we're going to keep it for 5 years and calculate its value. So what the formula says is that the value after 5 years is going to be equal to the initial value of the truck, $65,000, times 1 minus the rate at which it decreases, and it's going to decrease at 9% per year, remembering to change percents into decimals, and then we're going to keep this truck for 5 years, so t is equal to 5. We do PEMDAS, so we subtract 1 minus 0.09. We raise 0.91 to the 5th power, so 0.91 to the 5th power is about 0.624, 0.624 about. That's, I guess I'm rounding there. And then I multiply that by $65,000. And again, a little bit of a round, but we're at about $40,562. So after 5 years, that brand new $65,000 truck is worth $40,562. All right, so in general, the value of a truck decreases over time. All right, so it follows what we called yesterday an exponential decay curve. Okay? All righty. Then what I'd like to do is I'd like to switch to money. All right, and we're going to make a small adjustment. Yesterday we had our exponential growth equation, which looked like this. And what we do is we make a small change to our formula when we start to talk about money, right? And so the formula changes just ever so slightly. It still has an a sub t, it still has an a sub 0, it still has parentheses, it still has an r, and it still has a t. But we introduce one more variable. We introduce this variable called n. And n, the only thing that's changing now is this variable n, is called the compounding value. And what we mean by that is n represents the number of times per year that someone makes the calculation about the money, right? So if we were investing money in a mutual fund, if we were investing money in a savings account, if we were investing money in a certificate of deposit, N is the number of times per year that we make a calculation as to how much money is in the account. So sometimes that value of N might be 4. So some examples might be 4. That's called quarterly. Once per quarter or once every 3 months, someone makes the calculation. Sometimes these compounding values are 12, meaning once per month. But they can be all kinds of other things as well, including 365. Of course, 365 would mean somebody or some computer is making the calculation every single day. Okay? So these compounding values can vary quite a bit. So when you see problems, when you try problems in the assignment, they're going to tell you what the compounding value is. Okay? And so if we do an example, all right, the example I used back when you guys were in Algebra 2 was that we had someone with a birthday and somebody got a check from a long-lost aunt or uncle. All right, and let's say they get this long-lost check from an uncle or something, and let's just pretend that you work at a job for a long time, and you're able to save up $4,000 and you want to invest it. Let's say you invest it in a mutual fund, and the last time I looked up a mutual fund, it was making about 14% per year, which is probably a little on the high side now the way the market's going, but let's just stick with that just for kind of a fun thing. And then let's have a mutual fund that makes the calculation 12 times per year, so once per month. Okay? And finally, let's leave it in that account for maybe, let's start with 10 years, just so you can get a feel for how much it would increase. Okay? So what we'd be looking for then is the amount of money we have after 10 years. If the initial amount of money is $4,000, the rate of increase as a decimal would be 0.14. The N value is 12, so we're compounding 12 times per year, once per month. And then we're going to raise that to the time value multiplied by the N value. All right, so once again, it just becomes a PEMDAS. We just have an extra operation going on inside. And then instead of raising it to the 10th power, we're going to raise it to the 120th power. Okay, but let me do the calculation inside for everybody. 1 plus 0.14 divided by 12. If I punch that out okay, I got about 1.01166. So I'm going to raise that to the 120th power. And we get something along the lines of 4.022. And then we multiply that by 4,000. And in that mutual fund, then we'd have $16,089. Right? So after 10 years, the amount in the mutual fund would be $16,089. Okay? Just for a little variety, let me draw a little droop down the side here. And just to get you a better feel, as you get older and you get a job out of high school and get a job out of college, whenever it might happen to be, people are going to ask you to save for your retirement. And so let's say you get out of college at 22 and you're going to work until you're 65. From 22 to 65 is a period of 43 years. So let's say we take that same $4,000, and of course you'll actually be contributing a lot more, but let's say we take that $4,000 and we leave it in that mutual fund for 43 years. Still calculating the interest once per month, so an N value of 12, okay? So how much money would we have after 43 years? Well, of course, 1 plus 0.14 divided by 12 is still that 1.01166. But now 43 times 12 means we're going to be raising it to the 516th power. And it's just going to take me a second to punch that into my calculator, so give me a second here, guys. All right, and now I've got to raise that to the 516th power, which would get me 397.48, give or take. I'm starting to round now. And then when I multiply that by 4,000, we would have then $1,589,935. So that $4,000 that you may have saved up from your summer job and invested, or you got from a long lost uncle or aunt, right? If you left it in there for 43 years from the time you graduated from college till the time you retired from working, you'd have approximately $1.6 million. Okay? Just kind of showing you the power of investing, saving money over a long period of time. Okay? And finally, there's one more equation. There's one more equation that I need to give you guys, which will work for both money and other situations where the exponential growth, is called continuous. So we don't calculate the growth once per month or once per week or once per day. It just goes on continually all the time. And the last equation then that you're going to need from this section talks about continuous exponential growth. And it starts off looking the same as all of the others have. A sub t equals a sub 0. But now instead of the parentheses and the 1 plus or the 1 minus and all of that jazz, now what we do instead with continuous is we use the natural base e raised to the r times t power. Right? R is still going to be the rate expressed as a decimal. T is still the amount of time. But now our equation has actually become a little bit easier, excuse me, a little bit easier to look at. Okay? All right, and then let me give you an example of a continuous exponential growth. All right, so here's an example. City's population can be modeled by the following equation. P for population at time t can be modeled by 450,000 times e to the 0.08 t power. Okay? And so what I could ask you then is the following. Since population is going to be increasing continuously, then I could ask you, what's the population of this city at the initial time? So what's p of 0? So what you do is everywhere you'd see a t, you'd put in a 0. So let me highlight that so you can for sure know where I put that in. So everywhere you see a t, you put in 0 and do the arithmetic. So in this case, 450,000 times e to the 0.08 times 0 power, and what we get is 450,000. The idea is anything times 0 is 0, e to the 0 is 1, and 450,000 times 1 is 450,000. But then we could use this equation to make a prediction in the future, like what would be the population 20 years down the road? So P of 20. So once again, wherever we see the variable, we're going to replace it with, this time, 20. And again, let me choose the highlighter so everybody can see for sure where I put the 20 in. And we just do the arithmetic in that order. So we do 450,000 times E, and then we raise E to the 0.08 times 20 power. And what we get is a population then of 220, whoopsie, no, I missed a decimal, 2,228,864 people. So if you notice what the value actually was here, the value for R, The value for R was actually 8%. So if a city was increasing their population at 8% per year, a city with 450,000 people in 20 years would then have 2.2 million people. So of course, if you're a person who's working for a city, planning for a city, you would then have to make contingencies for housing and infrastructure to accommodate that huge increase in population. You have to be ready for that and plan for that ahead of time. Okay, so there's just a couple more application problems involving exponential growth and decay. A few more equations you need to get down and have ready to roll. Okay, so I hope you're having a good day, and I hope to see you. I hope I'm back tomorrow. Okay, see you soon.